Hello friends, starting with the same question. Find out the just coefficient coupling between the two plates coils which has the inductance L1 and L2. Now to take the two magnetized coils, that is coil A and the coil B. Both the coils have the turns like N1 turns in a coil A, and the N2 turns in a coil B. So the number of turns is indicated with the N1 and N2. These are the two inductances. The first one is the self inductance of the coil A is measured in L1, self inductance of the coil B, that is L2. So for L1 equals to N1 square by S, and the inductance is measured in a Henry. It's the same like the L2, that one is N2 square by S Henry, where N is a number of turns, S is a reluctance, and L is an inductance. So these are the three terms which are used in a magnetic coil. See the figure where the first one is a coil A, the flux is phi1, coil B, the flux is phi2, the current passing through the coil A is I1 and the current passing through the coil B is I2. So now according to that figure, we just gone through the further process and just find out the mutual inductance between the two coils, coil A and the coil B. The case 1, when the I1 current passing through the coil A, then the flux phi1, there is a certain notation, but it's nothing but the flux phi1. It's generated in the coil A. So phi1 equals to I1 into N1 by S Weber. The flux is measured in Weber. Again I am repeating, the flux phi1 is produced when the current I1 is flowing through the coil A. The amount of flux generated in the coil depends upon the amount of current passing through that coil. So if the current amount of the current is increased, then the flux generated to particular coil is also increased, and it is notation with the phi1 equals to again I1 N1 by S. Now assume that the K1 parts of the coil is connected with the coil B. It means that the sum of the portion of the coil A is connected with the coil B, and that portion is indicated with the K1. So the mutual inductance can be right like that. So whatever the inductance generated with that sum of the portion, that is indicated such like that. The M equals to N2 because the sum of the K1 portion of the coil A is connected with the sum of the portion with the coil B. So that mutual inductance is represented with M equals to N2 into bracket, N2 is indicated with the coil B, turns of the coil B, and the K1 phi1 by I1. So we can write like that, M equals to N2 K1 I1, K1 by I1 plus into I1 N1 by S. You can substitute the value from the equation for the previous equation. So ultimately we get that M equals to N1 N2 into K1 by S. This equation directly represents when the sum of the portion of coil A is connected with the coil B. Now the case number 2. When the I2 current passing through the coil B, so due to that the flux phi2 is generated in the coil B. So phi2 equals to, we can write like that, I2 N2 by S Weber. Now again I predict that suppose the sum of the portion like K2 of the coil B is connected with the coil A. So the mutual inductance due to that can be write like that, M equals to, now N1 is related to the coil A, but the part of the phi2 is right like that, K2 into phi2 by I2. So rearrange the equations are like that, M equals to N1 into K2 by I2 into I2 N2 by S. So now rearranging or by mathematical solving that, we can write like that, M equals to N1 N2 into K2 by by S. This one is case number 2, or the equation 2 for the case 2. Now taking the multiplication of equation 1 and equation 2, because we have to just find out the coefficient of the coupling. So that's why we have to just couple some of the portion of coil A and the coil B with each other. Now taking the multiplication, we can write like that, m into m, that is m square, equals to, where m1 is n1 n2 by k2 into by s, into m2, that is n1 n2 k1 by s. So m square equals to k1 k2 into n1 square by s and n2 square by s. So this one is the coefficient of the coupling. So now we just know that L1 equals to n1 square by s and L2 equals to n2 square by s. So instead of n1 square by s and n2 square by s into equation of m square, just substitute the value of L1 and L2. So we just get that m square equals to k1 into k2 L1 into L2 here, where L1 equals to n1 square by s and L2 equals to n2 square by s. Now just solving that m square, instead of m square we can just write like that, m equals to under root of k1 k2 into under root of L1 and L2, or you can just take the whole square of k1 k2 and L1 and L2. Now let that under root of k1 k2, this is the constant, so instead of k1 and k2 individually write, we can just put the common for the k1 and k2, we can write like that k. So it becomes that m equals to k into under root of L1 and L2. This is very important equation whenever you are connecting or whenever you are taking the coefficient of the two coils which has the inductance L1 and L2. So again I am repeating that whenever the two coils, coil A and coil B, or the sum of the portion of the coil A like K1 is connected with the coil B and some of the portion like K2 is connected with the coil A, then due to that the coefficient of the both the coils, it's right like that, m equals to k under root of L1 and L2, or the k is a coefficient, so we can write like that, k equals to m by under root of L1 and L2. Here the k is the known as the coefficient of coupling. Now there is three kinds of possibilities or the conditions. If your k is a 1, or your k is 0, or your k, the value of the k is between 0 and 1. If your k is 1, then both the coils are strongly bounded. So you can say that both the coils are strongly bounded with each other if the coefficient of coupling k is 1. If your k is equals to 0, it means that both the coils are separated with each other. So no portion of the coil A and coil B is connected with each other, or there is a vast difference between the two coils, or if the value of the coefficient is between the 0 and 1, it means that it's not separated with each other or they are not strongly bounded with each other, but we can say that they are mediumly connected with each other. This is the coefficient of coupling between the two coils. Now the next question, derive the formula for the energy stored in a magnetic field, and which amount of the energy stored in a magnetic field, how much amount of the energy stored in a magnetic field. Starting with the question. Now take the coil which has the inductance L Henry. Henry is the unit of inductor, that is L, or you can say that it's a coil. Now assume that whenever the current passing through the coil, it reaches to the 0 to I ampere with the same rate. The time period is same and takes the time with the same rate starting from the 0 ampere to the I ampere. So the electromotive force EMF generate in a coil. Whenever the current passing through the coil, the EMF is generated in the coil, and that one is right like that, E equals to minus L di by dt. This is the amount of EMF generated when the current passing through the coil. Now the applied voltage V drop across the resistor R should be balanced. It means that whenever the current passing through the coil, there should be one resistor that should be put there, because the voltage drop across that should be maintained, or your device may be damaged. And also should be balanced, it means that should be maintained. Also I mentioned about the EMF should be removed. So it means that the whatever the remaining the EMF can be removed with using the balancing the voltage drop across the R. So it should be right like that, V equals to IR, voltage drop across the resistor R, plus L dI by dt whenever the current passing through the coil. Now multiply the equation by I dt, V into left with the left side and with the right side multiplication with the I dt. So V into I dt equals to IR, voltage drop across R, also multiply with I dt, plus L di by dt whenever the current passing through the coil, also multiply with the I dt. Now you can write like that, V equals to I dt, IR plus into I dt, it means I square R dt plus L I di, because dt and dt are cancel out, so you can write like that, I into di. Now there are some parameters like V into I dt, I square R into dt and I into di. These are the three parameters. The first parameter, V into I dt, says that the energy given by the source, directly it reflects the energy. The I square R dt, which is the heat produced at the dt time, because I square R is nothing but the P. So you can, instead of you can write like that I square R dt, you can write also P into dt. This one is the heat produced. L into I di, the stored energy in a magnetic field, because L is mentioned with the magnetic field. So these are the three parameters. Now, so when the current is increased from the as we already talked with the earlier, starting with the earlier, with the same rate the current is reaching to the 0 to I ampere. So now just find out the value for the stored energy, taking the integration from the 0 to I ampere. So energy stored equals to integration 0 to I L I di. So equals to L, L is a constant, so just keeping outside the integration, so we just get that stored energy equals to L integration of 0 to I 0 to 1 into I into di. The stored energy, now put the value of solve the integration or making the limit that L equals to I square by 2 minus 0 with respect to di, taking the integration. So I integration for I is I square by 2. So stored energy becomes 1 by 2 into Li square joule. This is this energy stored in a magnetic field whenever the current is passing through it and it reaches to the 0 to I level. This is one videos taking from the technical education department, and this is an important video whenever the two coils are coefficient of the coils or the energy stored in a magnetic field. This is a magnetic coil and supply V, and there is a S switch S. One by 2 Li square, which already we proved that. Just skip this one. Now the next question, that is a question number 3b, which is one example. Whenever the two capacitors A and B are connected in series across the 100 voltage supply, and it is observed that the potential difference between them are 60 voltages and 40 voltages, because in the series form the voltages are different. Now a capacitor of the 2 microfarad is now connected in parallel with the capacitor A, and the potential difference across the B rises 90 voltage. So the calculate the capacitance of the A and B. The figure is such like that: two capacitor A and B are connected in series. The capacitor A and capacitor B are in series. and 60 voltage and near about 40 voltages are applied across that capacitor A and B. Now with the parallel of A and B, somehow capacitor C is connected with the parallel, so the voltage across that is somehow like 100, so the voltage capacitance of B is right to the 90 voltages. So now just find out the capacitance for A and the individual capacitance for B. Now assume that the two capacitors CA and CB is be mentioned in the figure. So case A, that when both the capacitors are connected in series, like in figure A, suppose we are just saying in a previous figure, when both the capacitors are connected in series, then the charge of them is the same, because charge is a Q equals to C into V. The current passing through the series circuit is the same, but the voltage is generated for both the coils capacitor are different in a series circuit. Q is a charge, so Q is a charge in a particular capacitor is same, so Q equals to C into V. So for the case capacitor A, it is CA into VA, and for the capacitor B, it is CB into VB, and both the value of that charge is same, so we can write like that: Q equals to CA VA equals to CB VB. Now Q charge across the voltage across the A, that is 60, and capacitor for the B, that is 40. So we can write like that: 60 CA equals to 40 CB, where VA equals to 60 and VB equals to 40, as mentioned in the figure. Yes, the voltage is this one is your VA and this one is your VB, and due to that the capacitor is CA and this one is capacitor is CB. So by taking the ratio CA and CB, we get that 40 by 60 equals to 2 by 3, because by taking the ratio 40 and 60 we can get that 2 by 3. So ultimately we get that CA equals to 2 by 3 CB. Now give the equation, the value of that in equation number 1. Now we take the case number 2, when the parallel